Okay, yeah. So then I will just do the second talk in this group, and most probably a lot of the stuff what I will tell you we have heard already previously in Niels' presentation and in the introduction. Nevertheless, as promised, I will take a little bit of a different approach as well and tell a bit about the journey to getting to these results and some of the difficulties and learnings we had so far. And I also just brought some entertainment slides, because you might also wonder, why am I here? So I'm from Siemens Energy. Why are we at this automotive conference? And so yeah, let me just like super briefly tell you. So we do sell solutions for power generation. So from a small, just from a small component or a larger component, as the large gas turbine, to the full power plant. So I'm working in the area of the large gas turbines, so really for power generation at large scale. And so there we are really looking at power outputs of like 600 megawatts. And actually also sustainability, of course, H2 burning are also huge topics for us. Then I also have to mention that the headquarters and the main facilities in Berlin, and the city center of Berlin. I can only recommend everyone, if you are in Berlin, come and visit. It's a beautiful historical site. There are gas turbines being built for more than 100 years. And so it's just a very nice place with beautiful machines being assembled there. Then coming already a bit closer to the topic of AI/ML. So we do actually have a lot of experience when it comes to big data and handling a lot of data, but we do have most of this experience when it comes to experimental data, sensor data. So most of our units which we sell, they do have sensors installed. So we do have a great experience with handling petabytes of time series data. But actually then when it comes to simulation data, we are not so good. So there we have to catch up actually on our testing colleagues. Because what I want to talk about today is rather what can we do with simulation data. And I mean, Neil has already mentioned, so for AI/ML in the whole average or in the whole CAE, there are so many different applications, from generative design to smart initialization. So it's a lot. But when I personally think about AI/ML and CAE, I immediately have to think about this, getting field predictions. So we have seen, it's also from the DeepMind paper, the video. And then that's something from Toyota research, where they already have this generative design, the speech, multimodal models for converting speech to designs. And then I have to say, so for me at the end, I really, at some point in time, I want to have my own personal engineering assistant who is, I will just go to work and tell, okay, so what do we do today? And help me design something. And when we think about this, actually, in what does this mean for specifically now turbine design, and what do we actually need to get this kind of smart engineering system? So there are different portions what we need. So we do need the data, we do need large language models to get this interface. We do need generative design, but we also need to have some kind of predictive ML. And that's what we are going to talk about today. And then we were also talking about this already. So is this heretic question of is AI going to be the next simulation, the next CFD? Is it going to replace it? And I have to say, I really see it more as an analogy between simulation and experiment. And I didn't know that the sound. So so let me just tell you this. So I really think that what we are seeing now with the new AI methods is similar to what we have seen with simulation a few decades ago. And there are a lot of questions around this. There needs to be a lot of experience and trust needs to be built. And of course, we need to learn the limitations of these methods, but they will come, and it's about how to prepare for this. And it's not about replacement, because I think what we have seen is actually also simulation. We are still relying a lot on experiments to do proper validation, and this is actually even more true now for the new AI methods, because if we really want to train models at large scale, then we need high fidelity simulation results, which are reliable. So that's actually a super important topic. Okay, so then why am I here today? And that's actually so for us it's a great portion just about blade design, because the turbines, they don't change dramatically. It's rather very small changes in the blades which have a small impact on the efficiency. But when you look at the power output of 600 megawatts, the small impact on the efficiency has actually a huge impact. And so we just do see simulation, and now also AI and the surrogate models at all. We just see it as an enabler which will give us the opportunity to make our products even better. And so we actually look at different areas of applications for this. So I think the one thing what is pretty obvious and everyone's like interested in is the time to market. So make design decisions as early as possible in your design process. But then for us, it's actually also about a lot about deviations. So how big is actually the impact of small deviations which are induced due to manufacturing processes? And that's actually something where we need to be able to make a decision fast, and we need to be able to evaluate this impact just purely based, for example, on a scanned geometry, which is completely different from a parametric typical CAD design with what you would usually work in your usual CFD process. And then, of course, we also have the topic of digital twins. So, yeah, I mean, that's also a topic everyone hears, but so here we are really interested in predicting the remaining lifetime of our parts depending on the real operating conditions the engine has seen, and where in the engine is this part positioned. So these are the main topics, and these are actually also the drivers why we are looking into surrogate modeling. Oops. Oh, what did I do? But until Ben has brought this up again, I just need to go back very to the front. I don't know how I did this. No, yeah. I will find it. How did I do this? Sorry for this. And just like the only thing what I wanted to say last, and that's probably the same for most of the companies. So let's say surrogate modeling for just predicting scalar values, for predicting KPIs. That's something what we have already very well established. So all of our processes, simulation processes, they are very well automated. So this one we can already make a check mark. Surrogate modeling for scalar predictions also a check mark. But now we actually really want to go one step further. And so the motivation for us actually to do this kind of studies is not that we necessarily want to develop and implement our own code for doing this. So we rather buy than do this on our own. But as I said previously, I really think that it's super important to do some of these things on your own just to learn about the limitations, what is possible, and what does it actually mean to apply this. So we just tested different models, which are which you can find in the literature. So all of these come from papers. So we also looked at the MeshGraphNet, same paper Neil has also referenced. Then we looked at the PointNet, which is actually more, or was initially more meant for object classification and segmentation. Then we also looked at the PointNet++, which is like the next iteration of the PointNet, which is supposed to be essentially good, or looking at multi-scale things. And then we also looked at the U-Net with the voxel representation of the geometry. And so then that was like the first finding. So this one, it's not really applicable. And that's just something that's like the first learning what I will share with you now. So when we look at the different geometry representations, so we do have the mesh, we do have the point cloud, and this is actually what a voxelized geometry looks like. And I mean, it's like super coarse, and you are already asking yourself, so how would you be able to really represent, like, especially because we are looking at small geometry changes in the blade. But then when we looked at the training results, and the loss curve looked great, and then as you can see, was similar to what Neil had also shared before, actual versus predicted, it looked amazing, and the R-square values were also great, and we were like, that's like really strange. But then if you think about it and you look a bit closer at your data and how it is actually represented, then you see that just by already doing this pre-processing of your data and of your geometry, you are changing already the values and the fields so much. And that's actually a change what you will not see in the typical machine learning KPIs, because when you compare this predicted to actual, it will just take into account the already processed data. But this change, what you have introduced before, that's not represented in the typical KPIs. So it's just important to be aware of, what have you done to your data even before you started the training? And you might need to take this into account. Okay, then coming to the Windsor and the DrivAer datasets and what we have trained and what data have we used. So for both of these data sets, we did an 80-20 split for train and test. We were looking only at the surface fields. So we did not take volumetric data, but we also didn't do the, as Neil was introducing, the direct KPI prediction. So we were just taking into account the surface fields and then deriving the KPIs as the drag from the fields. We actually did a high downsampling to fit this onto the hardware we have. So for the MeshNet approach, we did a remeshing, and for the PointNet, we actually just did a downsampling of the points. And that's also something what we found out during the process. So that's also something what I want to share with you, because this downsampling, you can do it in multiple ways. And there are maybe better ways and not so good ways to do this. So, for example, what we did also initially for the point cloud, just a pure downsampling of the points, which does not include like a proper interpolation of the values. So there's no surface averaging included. So basically, we introduced already an additional error into our data even just before we even started with the training. So also here again, it's just important to be aware of this. What you do to your data, even before you bring it to the model, it's important. Then when we talk about the required resources, I think it's also just important to be aware of everything what comes with it. So it's the data pre-processing, what you need to do to prepare your data for training, but then you cannot forget that every time you want to run a prediction, you have to apply the same kind of pre-processing to the data for which you actually want to get a prediction. So this also just means these are requirements for your computer environment, what you have, and so it might not necessarily be everything available on the same system where you usually run your simulations. Then for the model training, so yeah, as I said, for the MeshGraphNet, with a 90% downsampling, so even this was running on 6 hours on 4 NVIDIA 810. So yeah, also I don't know exactly about the cost, and I rather do not look it up because probably my colleagues will also hate me for this because we do have some budget, let's just say it like this. Then for the PointNet and the PointNet ++, we did a even harder downsampling because with this we were able to fit it onto some on-prem machines. But yeah, it's also this, it's just important to have in mind. And I mean, of course, here also, keep in mind that the software which we build, it's no professional software. So most probably there are ways to make it more efficient so that also bigger problems fit into less GPU RAM, but still there are limitations and you need to make sure that you have access to the right resources for the problems you actually want to solve. Then you also need resources to do the model prediction and the data transfer and storage. It's actually also, I mean, it's not trivial. So you also need to care about this. And there actually, I think, especially also in large corporates, none of these things at large scale you can basically not do without the support of IT and cybersecurity to really make sure that you do it the right way and that you not just, I don't know, upload your data which is under NDA to whatever and do stuff. Okay, now looking at some results. So I will start first with the Windsor body, and I will just present results for the PointNet approach and the PointNet ++. And yeah, you will see a few of these findings we have actually also seen before with Neil. So here I'm just showing the loss curves for CP and C and CF and X direction. And what we can see is, the one thing is it's quite noisy. And then on the left-hand side, we can see a typical case of overfitting. So it's not like super nice. And that actually we can also see. So here we do have these actual versus predicted plots. So we actually did not do it on the drag value, which would have been the more proper way. So our KPI, what we are looking here at is just a mean CP value. So just to be aware of this. And then what we can see actually already here on the right-hand side and on the left-hand side, so that's just, the blue dots are just the test data set, and the orange ones are data sets which we chose now for showing some contour plots. But you can see already that the spread is like, it's super large. So now, I hope you can recognize at least something. So it's all scaled, of course, also to and normalized. So you can always see like ground truth versus predicted, and then the error of the prediction. And you can see there are quite some errors, especially when we look at CP. So these results were not really nice. So that's actually also the point when we already decided to go further with the PointNet ++. So here we can see some of these losses for the PointNet ++. And so here actually it's even more obvious. So there are just some points which are like very, very far off. And that's actually also something here what we can see in the CP. And so I do also agree with Burka that looking at these kind of colorful plots, it does not really tell you something like really trustworthy about the results, but it will give you already an idea if something is like really wrong, like in this case. And this, for example, just made us look a bit deeper into the training data set itself, have a proper look already at the distributions of the values, and do a proper or more proper job in outlier removal. And so what we actually look, for example, is over all of the data sets for all of the cells of the surface, look at the CP value. And what we can see is that there are some strange values, which most likely also make this, despite the large changes in geometry, an even harder job of doing these predictions. So yeah, that's definitely something you really need to do a proper data exploration and filtering, cleaning of your data before you even get started. Okay, so now I'm already at the DrivAer test case again for the PointNet. So results again do not really look great. Again, the loss curve is like super noisy, so it's just not the kind of nice convergence you would like to see. And yeah, so the same also for the CP. And here there are just some results where you can see it's like really off. We do have a lot of errors. But then again, also here we did some data cleaning, we removed some outliers, and then suddenly everything looks already a lot better. The same clean data set we also used with the PointNet++. This even looked even more better. And so, yeah, like the last thing I just want to share is, so when we put this into the same kind of plot, then actually with the integrated force over our predicted surface, we lie within the range of other CFD results. Whereas again, to keep in mind that our ground truth is actually not the experiment. Yeah, with this, I just want to close and already say, so if at least this should be a motivation for all the proper software companies to participate the next time and show us that this can be done actually much better. Okay, yeah, then I wanted actually also to share some results from the MeshGraphNet, which I'm actually think it was the most promising, but then I kind of ran out of time and students, and yeah, so. Yeah, okay, so then last slide, just some learnings, and I think I've covered everything actually already. So really important is have a clear hypothesis. What do you actually want to do? What are your inputs? What are your outputs? Which formats does your data have? What size does your data have? Do you have the right resources? Do you need to contact IT or cybersecurity to really make sure that you are allowed to do what you want to do? Yeah, and then look at the data processing, think about what change do you already introduce there. Then the typical machine learning KPIs, they do not take into account this data processing. And then the question, like, what metrics do you really want to look at to get an evaluation of the quality of your results? It's probably not contour plots, but rather some line plots, which will really show you some characteristics of the flow. And yeah, so also bear in mind the data uncertainty, as we have talked already a lot about. Yeah, and then I think it's also super important later on when you have your model and you run predictions, you need to have some kind of confidence indicator as well, which will tell you, okay, am I still interpolating? Am I still like in a valid range with what I'm now asking the model to do? And yeah, I think that's it. So I just want to say we need to get ready. Yes.
Time. So
Yeah.
okay, if we maybe take the questions in the lunch break.
Yeah.
That's okay.
So ask me in the lunch break.
Yeah. Okay. Thank you.